My name is Zhang. I'm the Vice President of Applications. Briefly about myself. In 2006, I was a part of the team at the International Rectifier, working on GaN products. International Rectifier was the first company to invest heavily to commercialize GaN technology. We predicted that the project will be completed within 3 to 4 years. In reality, the technology was harder to develop, and the market timing prediction was off by 10 years. So in the GaN industry, we're being regarded as the grandpas. So actually, quite a few of the early grandpas joined Navitas. So we're very happy after 17 years, the GaN adoption finally takes off. In our early days of Navitas, we have noticed only about half the committed project together with the customer ever got to production. There are many project failures at last minute, mostly due to the technical issue or due to the delay of the schedule. So you can see that the power supply design is quite complicated. It has about easily 100 components to thousands of components. When we use GaN to have a high density design, there are lots of new things, new components get put together into the system. So that creates lots of uncertainty, and there are lots of same learning happening from one customer to another customer. So we decided to help the customer and consolidate all the learning. So firstly, we created the mobile design center in Sheridan next to our key customer. So the process is basically we start with the business case with the customer, then we put together the finalize the target spec, all that, then put together the topology architecture with the right GaN product. And then we help them with the layout and put the whole thing together, complete the testing, make sure thermal, radio, EMI frequency, interference will be okay, and get a safety certificate. Then even during the early production, we still have to help them babysit all the way to resolve any yield issue or any process improvement. So we have to do this iteratively and to get it to work. So far, it's been very successful. And right now, we have 3 design centers, mobile, data center, and data center power, and the EV. So the data center, the design center, system design center is a critical part of Navitas' go-to-market strategy. So this is one example. We designed hundreds of adapters to the market. This is just one snapshot of the mobile laptop adapters. As you can see, there's so many customers. It should be very obvious to you. There are no 2 adapters look alike. They're all different. The customer always wants their own form factor. They always want their own power level, right? So we try the standardization with them. They don't want that. They want their own customization. So to do that, many times lots of projects get delayed because the marketing of the customer wants around the corner or some other things, make it flatter or a cube looking or anything in that nature. The repack on the component many times requires a system redesign. We have all the toolkit. So it's a problem for the customer, but it's a really good problem for us to solve because we have all the toolkit. We can get it going pretty rapidly. So we'll give you a few latest platform examples we developed together with the customer. So this 140-watt design is a benchmark PD adapter. The PD basically is the reason adapter took off is because this standardization of this digital interface between the adapter and the load. Then once you have that standardization, you can get to high power. You can charge all kinds of devices with the same adapter. So traditionally, the power top to 60 watts, then later to 100 watts. With the PD 3.1, right now, the market, the highest power is 140 watt. When you get to 140 watt, you can use that to charge many mobile devices. So 140 watt is a state-of-the-art. It's made of GaN, it has a GaN component in there, our GaN component also in there. So we say, how can we make it better, right? Just say, this is the benchmark today, can we make it better? So what we did is that we look at the system, they're using a 3-stage power conversion with our latest component. We can do 2-stage to save 1-stage power conversion and associated cost and efficiency penalty. And you made the system 25% smaller. And most importantly, it's $2.80 component cost reduction. That's like a 10 to 15% of system cost reduction. So there could easily be a refresh of the same product in the market due to the mostly cost and size benefit. Talking about the PD 3.1, the standardization, the power actually can go all the way to 240 watts. The next one to be introduced to the market will be the 180 watt PD adapter. It has more power. The size, the key performance target is that for mobile adapter to charge all kinds of mobile components, it had to be small. The adapter must be small enough to be in your suitcase or even carry with you, right? So if it's too big, then you stay home. Then you won't be able to serve its purpose. So this one, as small as the 140 watt design showed before, and you can deliver much more power. And the 180 watt, you can charge many components, like a fast laptop, gaming laptop, and even some of the monitors, lots of other things. So this will be a next wave in terms of the power adapter. Another example, I just show you working with a leading OEM company. For gaming, there are lots of advanced on gaming laptop. The 300 watts is a popular power rating for the adapter. It's too big. The one shipped with together with OEM laptop, it's very bulky and heavy, almost as heavy as the laptop itself. So we have been asked a few years back, asked by the OEM to reduce that by half, reduce the size by half, such that you will make the whole system look very appealing. So we achieved that. We chose the right architecture at that time and the right component to reduce the size by half, and at the same time meet all the thermal safety, all the regulatory requirements. The problem with that, even though you get to the production, it's just a little bit too expensive, even expensive for the gamers. So it's not hugely successful at that time. Then recently, with the learning we had, we tried to look at this again. So we achieved the same density reduction, and the efficiency and everything is the same as before, but we get the same cost of those bulky adapters. So we expect this to be popular for the gaming company. The example I just gave you from the mobile design center mostly was from the mobile laptop, right? So there is another competing cap for the same PD space. That's from the mobile phone company. They're also using a bigger adapter to charge your phone faster, right? They can get the phone charged within minutes. But at the same time, the actual power also can be used for charging laptop and other mobile device. So there are lots of those overlapping requirements from two competing caps, and lots of need for our design center, right, to address their customer need with the evolving need. We're very happy with how all the toolkit to serve both needs. So moving forward, that once we have the reliability verified and supply chain robustness confirmed, we move to the adjacent market. In response to the government mandate, energy efficiency mandate, there are lots of opportunity in the motor space, motor drive space. Motor drive space is extremely wide and extremely large, basically from 40 watt all the way to, for our space, 40 watt to 4 kilowatt. That's the first motor drive market we try to attack. It covers like consumer high-speed hair dryer, right, and also the refrigerator, heaters, and also the factory automation stuff. So lots of opportunity for us to either help with the density or the efficiency. The benefit of GaN in the motor drive is this. So you can see there are two traditional power switches using silicon. They all state at the 6 kilohertz. All today's motor drive solution running at 6 kilohertz. The reason for that, you can see the bar, there's the switching loss, there's the conduction loss component, but total is the power loss. You can see the moment it go up in frequency, let's say by 3 times, the penalty is just too big. Just the whole thing just become too hard and too unmanageable. So they stay on 6 kilohertz. Again, on the other hand, has almost no penalty. It's a very flat frequency curve. We can triple the frequency for the same efficiency, and also even with that and the high frequency, we're still better in efficiency over the today's silicon solution. So with this capability in mind, essentially we can remove the heatsink inside the motor drive to make the size smaller. And also for some motor, when designed properly, a high frequency switching allows the better wave shaping for the motor signal and allow the motor to run mechanically more efficient. So that 2% is a big number for the motor efficiency improvement. So this is a few examples of the reference design. This design was done in Europe by our AE team, application team in Europe. The first one using our half-bridge product that just introduced, very, very tiny, very small, and single-phase design, 150 watts, no heatsink. The size is about 2-inch wide in diameter. This platform has been successfully used in the consumer high-performance hair dryer product, shipping volume. The second one, using 3 of them, right, become like a three-phase configuration. This can do 500 watts. Also, similar in size comparatively, no heatsink needed. So those, and also we have other platform get us all the way to a 1.5 kilowatt, also with a similar size, with the latest component. So motor is a market we're engaging extremely actively, and we have a lot of engagement with the customer. They're perfectly okay with the reliability data we provided and also the performance we provided. Very impressive for them. The new product that I introduced, GaNSafe, we're going to demonstrate the capability of this part. Just to emphasize why this part is important, why the other part is not enough for this high power. High power customers are very conservative, right? They're okay with the GaN because of the proven reliability, but they're not okay with the brand new packages. We must use their proven package, so like a rugged proven package. They need that for like a thermal management and also for the like temp cycling. There's lots of special requirement. They don't want us to touch it. To put our platform into this robust package, we have to redesign our chipset, driver, and again, all that, and we did that very successfully. The input, the configuration, pin out, extremely simple. Compatible with the today's driver, no system, almost like a drop-in into the silicon socket. You can get it to switch. You can run very fast. And the reason the discrete GaN so many times, for so long, hasn't been successful in high power, mostly due to fuel problem, mostly related to the so-called ruggedness issue. One example is like a ESD. 2 kV ESD requirement is standard. Without any protection, the GaN discrete can only handle about 500 volts. You rely very, very careful handling in order to prevent the ESD damage in manufacturing. So obviously, we can easily meet that 2 kV requirement. The short circuit overcurrent protection for motor drive, any high power, is a frequent occurrence. It happens all the time. And the device has that inherent capability. The silicon carbide all have some inherent short circuit overcurrent capability, but GaN does not have any inherent capability, right? So they rely on the system to provide the protection, but that's not foolproof. If there's any delay, any noise, it just won't provide adequate protection. So we're bringing the inherent protection back into the chip, and we'll do the demonstration. You will see you can have a repetitive overcurrent short circuit event. The device is safe. It's just a peace of mind for the customer. So we have a family of this product. Also, we're engaging with the data center and the EV customers. So this is the last slide. Essentially, with a proven success in mobile and established reliability and field data, we are very comfortably moving to a higher power into the data center, EV, industrial applications.